Assalamu alaikum, student. I hope you are fine and doing well. Today, first of all, let me thank you all for attending my online lectures. Dear student, today our class is about linear transformations. And linear transformation play a very important role in computer graphics and computer vision. The today the when we are saying that if you visualize some 3D object and you transform this 3D object from 3D to 2D, means to say I'm discussing computational photography. I mean, the visual world is three-dimensional, but the our actual picture is two-dimensional. If you can print some your picture, like you can take its print from printer, then the page will be two-dimensional. It means whenever we are seeing some three-dimensional object, basically our black cornea inside our eyes is two-dimensional, just black cornea. It's not just you take the whole um, eyes of yourself. Just take that one black cornea. This is two-dimensional, and the visual world is three-dimensional. So the in camera you have to design such a mechanism that fundamentally relate three-dimensional to two-dimensional. So, dear student, in that case, the idea of transformation is generated, and the idea of transformation is play a fundamental role in computational photography. Today I more or less discuss linear transformation, why linear transformation is so important, and then we will discuss some mathematical definitions, and then we will discuss how your a color images transform from three layers to one layer. I mean to say. Let me elaborate this with the help of one fact that the world in which we are living is consists of basically it is the world of sequence of continuous images. If I'm moving and I'm making any videos, it's a video is a set of frames, and uh, one frame is a one picture, and one picture, I mean to say it is a color image having three dimensions. And in three dimension, I mean to say red, green, blue. And corresponding to every dimension, I have a matrix of order m cross n, whose element are from uh, z uh, Z to 8, that is 8 dimensional, having element from 0 to 255. So each and every pixel of your image is fundamentally consists of 8 bits, and it ranges from 0 to 255. So if I can say 0, that if you can transform the 0 is a just decimal into binary, so you have 8 binary vectors. So if I can transform 255 into a binary, so you have 8 tuples of 1. So if you can transform 254, then you have 1 0 and 7 ones. In that case, student, if you can realize this is in this from in image from 0 to 255, if you convert each and every element from decimal to binary, you what you will get ultimately, you will get the element of z to 8. It means each and every element is 8 tuple, or every element is consists of 8 uh, tuples, and having z2 means to say it's are belonging from binary field. Z2 means 0, either 1. So I will discuss this about how your image can be transformed from grayscale to basically color image to grayscale, and I can write it as a linear transformation. How this transformation is performed in MATLAB. What is the mathematics behind your MATLAB function from RGB to grayscale transformation. So, dear student, I'm not going to waste your time. So let me uh, focus on what we will discuss today about. So, introduction to transformation. So, whenever we are saying transformation, it has some domain and it has some range. So, if I can say T is a transformation that maps some element of one set, say V to a W. So, dear student, we are all talking about n tuples. So, V is a n-dimensional vector set and W is a m-dimensional vector space. So it is, if I can write it down, T's are from Rn to Rm. So Rn has n tuples and Rw has m tuples. So dear student, if you can say this, V domain of T, set is V is a, this is a set V and this is a set W. As a whole, this is a range, and as a whole this is a codomain and this is a image of V under T. So dear student, if you can say this T is a mapping that map element of V into element of W. So let us these kind of things we have discussed in our previous figure. So RGB color space. So dear student, actually the things which are while you are taking any picture from your camera. See, camera is fundamentally based on RGB color, red, green, blue colors, and the television is consist of YIQ color space, and other like printer, scanner, and your printing media like your newspaper and your signboard are depend upon other type of color spaces. So I just take one color space in, there are several other color spaces, but I just focus on RGB in order to understand what is actually the idea of linear transformation in that. So whenever we are saying RGB, it means we have three layers. It is a color image, and color images consist of three layers. This is red, green, blue layers. So each and every layer is a fundamentally a matrix of M cross N whose element from Z to 56. So Z to 56, I mean is from 0. So it should not be 3. It should be, sorry, it must be like if you can allow me, then I can do it like it must be 2, then it must be also 2, it must be also from here 2. So and let me elaborate it. So dear student, if you can see this 0, 1, 2, 3, 5. So let me elaborate this one. So a red layer is consist of M cross N matrix. If I can say 1, 2, 3, 4, 5, so 1 2 3 4 5 6, 1 2 3 4 5 6. So this is a matrix of 6 by 6 having 36 pixel, and same green layer is of 6 by 6 matrix. Here M is 6 and N is 6 in that case, and this is first pixel, this is second, and it has 36 pixel. In that case, it is also a 6 by 6 matrix, and each and it has a 6 by 6 matrix, and this green layer is also consist of 36 pixel, and same is the case with the blue layer. So I can write red layer as a matrix of M cross N over Z256, where Z256 is 0, 1, 2, 3 up to 255. Similarly, red layer can be written as this, and similarly blue layer. So ultimately, in color spaces, we have a set of matrices. So if I can elaborate this with example, how your RGB to grayscale transformation is look like. So if I can take T, the transformation, that is, if you have one color image, this consists of three layers: red layer, green layer, and blue layer. And then from these three layers, you get only one layer. It means this color layer is consists of three matrices: one, two, three. Then if you merge this and this will generate only one grayscale color image, and which is consists of only one matrix. So if RGB to grayscale transformation, I mean to say it take three matrices and map on one matrix. This is a one matrix, red matrix. Uh, Corresponding to red layer, we have this matrix. Corresponding to green, we have this one, and corresponding to blue, we have this matrix. And when we apply some transformation uh, under T, these three matrices map on one matrix. Also, this is our transformation, that T is a transformation RGB. R is from this matrix, G is from this matrix, and B is from this matrix. Dear student, this is a actual transformation which I am going to exemplify in this slide 15. This is not just a just I given you example. This is the actual function. This one, like this one. So if you can say this one, okay, sorry. So this one, this is your actual examples. What I am saying that about this one, this one. So this function is basically used by MATLAB while transforming any color image, this one to a grayscale. So it takes three tuples, one from this matrix, second from this matrix, and third from this, and transform it to this. Like 0.33 R plus 0.59 into G plus 0.11 into B, and who take it as a floor. So one thing you must remember, this is also a application of a floor function. So I must cut it down the matrix of general matrix from 2 by 2. Say I have a matrix whose red layer is 2 by 2 matrix, whose element from Z to 55, another green, and other blue. So I have 2 by 2 matrix, color image of 2 by 2, whose red layer is consists of this one, blue layer is also consists of 2 by 2 matrix, and blue layer is also consists of 3 by 3 matrix. So the transform, well, we are applying RGB transformation flow. Point 0.3 first value 11 plus 0.9 the first values of green layer plus 0.11 and this blue values of uh, or first values of blue layer, that is this. While applying this one, and the result will be in points, so you take its floor, then you will get 17 4 seconds RGB. Then we again apply this function, 0.3 into 255 plus 0.59 into second element of the green layer plus 0.11 into 25. So you will get triple one. So ultimately I put a question sign, you have to do it by yourself. So ultimately, dear student, the thing which I am going to uh, giving you the idea about it is how your three layer is converted into a one layer. So this is the matrix transformation that transform your three dimensional matrices to one, basically one matrix of 2 by 2. So if I can write it down like uh, this is a three matrices, and that correspond to one matrix by using this transformation. So ultimately, this is one of the example, real example of um, linear transformation. So these are again some color spaces, and which I told you that there are number of color spaces: RGB, HVS, XYZ, U, YU, YUV is also used in color printing and in press media, or like your newspaper and etc. So, dear student, while you converting RGB to YIQ, it is basically a three-dimensional vector space to three-dimensional. So, this is a conversion. You take one 3 by 3 matrix and multiply the input with the input from RGB, red, green, blue, and multiply it with 3 by 3 matrix, you will get YIQ coordinate. So a T of V is equal to A into V. In that case, A is 3 by 3 matrix, and element of V from this one, which is red, green, blue layer, RGB. So YIQ from G. So you have to calculate the inverse of this matrix. If you calculate inverse of this matrix and multiply it with this one inverse of this matrix with this, so you will get RGB get back. So in that case, if I can say this is a YIQ to RGB, this is again a in term of transformation, TV is equal to NTV. Here I can say A is basically this one, and V is basically input from this one. So this is again a three-dimensional vector space. Uh, so, dear student, let us take one example, mathematical example, how you can take some basics of transformation. That you have a vector from R, two-dimensional vector space R, and T is a transformation from R square to R square. There are some function that is basically find the image of V, that is minus 1, 2. That's you plug minus 1 at this and 2 at this position, and correspondingly minus 1 at this 2, and then ultimately two input under if you have two input under T, this will also map on two input. Find the pre-image of minus 1 and 11. In that case, you have to calculate this pre-image. I means to say uh, then you calculate V1, V2, and you basically this is equivalent to this matrix of transformation, and its image is minus 1 and 2, minus 1 and 11. So you have to calculate its pre-image. I mean to say under what condition what will be the values of V1 and V2 pre-image. It means element of first in domain that give you these values. So ultimately, when by definition T is T1 V2 is equivalent to this one, and this image is basically this one. It is given over here. Find the image of V. Find the pre-image of W. It means it's the element in second set and in codomain. So its second element is codomain when the input this is equivalent to this one. So in that case, if you compare U component X component with X and Y component with Y, so ultimately you get V1 and V2 values. So these are the pre-image of minus 1 and 3. So I can say from this example is so this is the basically pre-image, and in that example you given the values of V, and you want to calculate under what condition I get this value, under what condition what will be the values of V if I have value of W. You can see over here in this example, we have values of W. We have to calculate this pre-image, that under what will be the values of in domain that give us this values in codomain. So these are V1 and V2. V1 and V2 which are equivalent to 3 and 4. So linear transformation. And let us define some proper definition of linear transformation. Let V and W be the two vector spaces. The the function t from V to W is called a linear transformation of V into W if the following two conditions hold. I mean to say t of U plus V is equal to t of U plus t of V. It means that either you have to calculate the image of u under t plus image of v under t and add them, and or if you first add u and v and then take st, both must be equivalent to equal. If they are equivalent, and if you multiply a constant with u and take its transformation, it is equivalent to if you take first transformation of u and then multiply it with c, they are equivalent. If these two properties are satisfied, then we can say the T is linear transformation from V to W. So keep one thing in your mind that that linear transformation preserve origin. It has some sharing properties like sharing, rotation, scaling. So, but always keep one thing in your mind. Under linear transformation, zero remain at zero, and lines remain at lines. So these are something. So let us elaborate the concept of linear transformation with the help of this matrix. If you can look over here, so it is basically vector addition, and this is again vector scalar multiplication under T. So dear student, once again, as I told you while discussing the idea of vector space and subspace, the whole linear algebra is evolved around vector addition and scalar multiplication. So this is again a vector addition under T, and this is a scalar multiplication under T. So let us elaborate the idea of linear transformation with the help. If you have two elements in domain and you apply T on separately on these two elements, that T of U comma T of W, T of U2, T of U1 and T of U2. If you add them, U1 plus U2 and take its linear transformation, that's it, T of U1 plus U2. And if you separately take this element and apply T, and you get this, and if you add these both, so one can say there is a two-way to reach that position, this position. One is you add these two and apply T to get this. Another one is you separately apply transformation of U1 and U2, that is separately, and then add these uh, image of T under U1 and image of T under U2 and add them, and you will get this. If the result is same, then we can say it is a linear transformation. Same is the case with multiplication. You can realize with this. You have a one element U, you apply transformation on U, you get T of U. If you multiply alpha with U, you will get alpha times U. And you can take its transformation, this transformation of T. That what you will get, T of alpha times U. And if you apply U, T on this U, you will get T of U. And multiply alpha with this output, and you will get this element, alpha times T of U. If these are equivalent, that is transformation from here to here, or transformation from here to here are equivalent, then in that case, if these two properties are satisfied, we can say it is a linear transformation. This is more or less quite comprehensive diagram to understand the linear transformation. So dear student, let us take one example. We show that T is a linear transformation from R square into R. So take two element from domain, that is R. U is belonging from R square, and V is belonging from R square. U are also belong from R square. Since it is belonging from R square, so is u and v is two tuples. So add these two vectors, we'll get this and apply transformation on these two elements. That is t of u1 plus t of u2, t of u2. If these are x coordinate and these are y coordinate, if here you can see in your actual transformation, which is given in this example, that when you operate t on u1 and u2, what it did, it take the difference of these two elements, x coordinate and y coordinate, then add first coordinate plus 2 times second coordinate. So this is, so like here, this is a first coordinate and this is second. Add first coordinate, subtract first coordinate from second coordinate. This is first coordinate and this is second. Like this is a first and this is second. This is first coordinate is subtracted from second. So this is a first coordinate, this is second. First coordinate is subtracted from second, comma. Then first coordinate plus 2 times second coordinate. This is a first coordinate, yani first coordinate plus 2 times second coordinate. So you can just rearrange u1 minus u2 plus u1 minus 2 times u2, then v1 plus 2 times u2 plus u1 plus 2 times u2. So if you can say this is one of the basic rule of coordinate addition. X plus y, z plus u is x comma z plus y comma u. If I can add these two, you will get back this. So I just take this one, this element, and this element, that is x and z. So I just I have this information over here, you can see over here, and I have to transform this information into this one. So I have this transformation over here, so I have to transform, like this is a x and this is my z. So x comma z, x comma z plus y, this is my y and this is my u. So x, this is y, which is u1 minus u2, uh, comma u. This is my u as a whole. If I can relate this with, this is first plus y, comma z plus u. This I take it as a whole u. So in that case, I just separate this, and this one is what? This is t of v1 plus this is what? This is t of u. In that case, I can say the transformation, I just start with this one and end up with this one. So first property of linear transformation is satisfied. So second one is I take scalar with v. So scalar time v is c of v1 comma v2, c of v1 comma c of v2, transformation of c of v. I mean to say I just apply transformation of this, and this is equivalent to this one, c1 v1 minus c of v2 comma c of v1 plus 2 of c of v2. I take c from common from this whole. I just here I just use my definition. I apply t on this one, t on this one, t on this. The output, when I multiply c with v, I get c1 v1. Then I apply t on c of v1. It means to say I apply t on these coordinates to coordinate. So this is my u1 and this is my u2 in that case. So once again you have to apply this definition. Take it as a u1 and this as a u2. So v1 minus v2, because this whole, treat this whole as a v1 and this c times v2 as a whole v2. So you just use this definition and ultimately you will get c everywhere. So take c as a common and c time, and this is what, this is again t of v, t of v. So in that case, both you start with T of C alpha C T of CV and end up C time T of E. In that case, both properties of linear transformation, I mean to say vector addition, this one, and scalar multiplication are both are satisfied. So T is a linear transformation. Dear student, sometimes it is quite difficult to show that all calculation. So there is another way that you have to, as I start my lecture, I told you one thing: in a linear transformation, zero remains zero. So in that case, if you put t of zero, then it will always map on zero. I mean to say in R square, the zero will be not just one element, this will be an order pair. It means 0, comma 0 is map on 0, comma 0. If this really happened over here with respect to this transformation, so this will always be a linear transformation. Let me check it out. So I have this transformation T of V1, comma, or previous example. So I take origin in R square. So 0, 0. So using 0, 0 origin in T, I means to say 0, 0, 0, 0. So this is 0 minus 0, 0 plus 2 times uses. So what does it mean? 0, 0 is map on 0. In that case, you can just say this is a linear transformation. This is one of the efficient way to check either some transformation is a linear or non-linear. So, dear student, when I say that when I say that linear in linear transformation, when I said this one that zero is map on zero and all other I should say all other things are zero is preserved and lines remain line. In that case, I must give you some overview of one of the simulation. If you can hear this one, like zero remains zero under t, and then we can say it is a linear transformation. Like this is one of these simulation.
Some vector and spit out and equalize this in moving over to the output vector. Then to understand the transformation as a whole, we might imagine watching every possible input vector move over to its corresponding output vector. It gets really crowded to think about all of the vectors all at once, each one as an arrow. So, as I mentioned last video, a nice trick is to conceptualize each vector not as an arrow, but as a single point, the point where its tip sits. That way, to think about a transformation taking every possible input vector to some output vector, we watch every point in space moving to some other point. In the case of transformations in 2 dimensions, to get a better feel for the whole shape of the transformation, I like to do this with all of the points on an infinite grid. I also sometimes like to keep a copy of the grid in the background, just to help keep track of where everything ends up relative to where it starts. The effect for various transformations moving around all of the points in space is, you've got to admit, beautiful. It gives the feeling of squishing and morphing space itself. As you can imagine, though, arbitrary transformations can look pretty complicated. But luckily, linear algebra limits itself to a special type of transformation, ones that are easier to understand, called linear transformations. Visually speaking, a transformation is linear if it has 2 properties. All lines must remain lines without getting curved, and the origin must remain fixed in place. For example, this right here would not be a linear transformation, since the lines get all curvy. And this one right here, although it keeps the line straight, is not a linear transformation, because it moves the origin. This one here fixes the origin, and it might look like it keeps lines straight, but that's just because I'm only showing the horizontal and vertical grid lines. When you see what it does to a diagonal line, it becomes clear that it's not at all linear, since it turns that line all curvy. In general, you should think of linear transformations as keeping grid lines parallel and evenly spaced. Some linear transformations are simple to think about, like rotations about the origin. Others are a little trickier to describe with words. So how do you think you could describe these transformations numerically? If you were, say, programming some animations to make a video teaching the topic, what formula do you give the computer so that if you give it the coordinates of a vector, it can give you the coordinates of where that vector lands. It turns out that you only need to record where the two basis vectors, I hat and j hat, each land, and everything else will follow from that. For example, consider the vector v with coordinates -1, 2, meaning that it equals -1 times I hat plus 2 times j hat. If we play some transformation and follow where all three of these vectors go, the property that grid lines remain parallel and evenly spaced has a really important consequence. The place where v lands will be negative.
So let us come to our lecture that in linear transformation, origin remain origin and parallel line remain parallel, and origin is always fixed. Means to say, if you apply some transformation on some input, that it should not change the origin. If you can say, if you put it if I can place, if you can allow me, how I can relate this. So, dear student, if I just change this one, so if I can change little bit about like this one, I can take another transformation I just add plus one. Sorry, sorry. I just add one over here. If you can see one. So in that case, dear student, if you can look over here, so if I put origin in this transformation, so what I get one, then this. My coordinate after putting 0, 0, I will get, when I put 0, 0 as origin, I'll get 1, 0. So in that transformation, origin is not fixed. Means to say, when I apply a transformation on the origin will be shifted from 0, 0 to 1, 0. So in that case, the transformation is not linear. It becomes a fine transformation. So, dear student, you must keep this thing as I show you one of the YouTube very small simulation of linear transformation. So this will be non-linear transformation, and we call it affine transformation. So in that case, if I add just one, so in that case, origin is mapped on 1, 0, and whenever some transformation we apply on origin and it does not give us 0, it means the origin is shifted. And in case of linear transformation like this example, origin should not be shifted. So let us come up with another definition like so. So if you can look over here, there's some functions that are linear or not. If you can place f of x1, x2 over here, this is not generally equivalent to sine of x plus sine of 2. So therefore, f of x1 plus x2 is not equivalent to f of x1 plus x2. So in case of f of x square, even it is also not nonlinear because it doesn't satisfy this property. If you can take another example like f of x is x plus 1, in that case, if you insert in place of x plus x1 plus x2, then x1 plus x2 plus 1. So if you can add x1 plus x2 like f of x1, I means to say, just place whenever there is you place in place of x, you place x, so there will be x1. So f of x1, I means to say f of x1 plus 1, and f of x2 means x2 plus 1. If you can add them, you will get x1 plus x2 plus 2. In that case, this left hand side is not equivalent to right hand side. In that case, this function is also a nonlinear. So nonlinear transformations. this is a non-linear. I take it as a transformation, not as a function. So treat these as a transformation, not function. So these are all non-linear transformations. So, dear student, let us zero a transformation, some basic definition, and transformation from V to V from vector space to itself is called linear operator. Zero transformation means to say whenever you put any non-zero element and it map on zero, then we can say it is a zero transformation. And identity transformations means to say whenever you take any element of domain, it give you the same element. So in that case we can say this is the identity transformation, provided that the range and domain are same. So let us say this is one of the property which we have used, that origin is a map on origin in linear transformation. If t is a linear, then this will happen. So rest of the properties you have to satisfy and realize by yourself. So these are again a linear transformation. T from V to W is a determined completely by the action on a basis of V. So if you have a basis vector, then you can apply T on V1, T on V2, T on Vn, and given then the T is determined for any V in V. I mean to say these elements can if these are belonging from basis, then one can say any arbitrary element of Rn. Basically, this is the element from Rn can be written as a linear combination of basis element, and you can apply separately T1, T2, and T3 and Tn to every vector given in basis element. So let us explain this. If you have a transformation from R3 to R3 with a linear transformation such that when you input t of 100, it will give you output 2 minus 1 4, and then t of 0 1 0, this will give you output 1 5 minus 2, then t of 0 0 1, that it will give you output 0 3 1. Find t of 2 3 minus 1. So dear student, this is one of the arbitrary element, and as I told you, if this arbitrary element, then it can be written as a system, can be written as a linear combination of basis element. Basically, these are basis element as we have discussed in case of R3. The standard basis element are 1 0 0 0 1 1 0 0 1. So dear student, if you can look over here, v1 v2 v, and basically these are v1 v2 v3. These are in this example, these are basically, this is v1, this is v2, and this is v3. So these are belonging from basis set, so it can be written as a linear combination of this one. So T, if you can apply T on this one, I just use scalar properties of linear transformation. When you apply transformation on this as a whole, the scalar will be can be multiplied and can be multiplied with transformation like this property. If you have a linear combination, V can be written as a linear combination of V n element. Then if you apply T on V, then C1 T of V1 plus C2 T of V2 plus so on C of T and Vn. In that case, if you can see over here, this is C1, this is C2, C3, and this is one vector which can be written as a linear combination of basis element. So dear student, these all C's are will be come out, and we apply just T on this basis element. In that case, if you can see T of its output is like this one, and T of 0 1 1, its output is like this one, and T of 0 0 1, its output is this one. So ultimately, you have to insert all these output and multiply them, and you will get 770, which is the output of 2 3 minus 2 under transformation T. So it means to say you get another position in three dimensions that map 2, 3, minus 2, 1, 7, 7, 0. So, dear student, linear transformation defined by matrices. If T is any transformation from R squared to R3, then I can say this I have T of V is equal to AV, where the order of matrix is 3 by 3 cross 2. This like you can take order of this can be seen with the reverse of this domain to range tuple, that it has three tuple, it has two tuple, the order of matrix will be 3 cross 2, 3 cross 2, so 3 rows and 2 columns. So I had domain element will be uh, 2 cross 1 element, because in R square we have two tuples. Two tuples I means to say column vector having 2 cross 1 column vector of order 2 cross 1. So T of V, where V, find T of V where V is 2 and minus 1. So you just put this and 6, 3, you will get uh, 3 tuples. So 2 tuple is map on 3 tuple. It means to say if you are in a plane and you just plane element in 2 dimension is map on element in 3 dimension. So, dear student, you take this as a homework, example number 5, and these are just read it out. And I can say, and matrix M and I'm defined as a linear transformation from Rn to Rn if AV is equal to the matrix is of order M cross N, and this is a element of domain that is Rn. So it is n vectors. So if you multiply, you ultimately get u1, u2, u3 up to un. This is the m cross 1 tuple. So each and every element is over here in Rn is m cross 1 tuple, and it means it has number of vectors, and every vector is basically m cross 1 element. So in that case, this is just meaning of this whole slide. So, dear student, what does it means? If you have this matrix and you are transforming any position of any particle with that make alpha angle alpha with x-axis, and you just rotate with theta while applying transformation t. So what you will get, so ultimately this point will be translated from this xy to this second point. So how we can perform it? So if you can realize this, if you can just take this array and resolve it into a component form, the x component will be this is a one vector having magnitude r. So the x component will be r cos alpha, and y component will be r sine alpha. So v is x comma y, r cos alpha, r sine alpha. So if you apply T of V A into V, because matrix of transformation in this case is 2 by 2 matrix, and which is given over here, so you have to transform this element which is of the form this. I just take this element as, if you can resolve this, this is a one of the column vector of magnitude r. If you can resolve this vector of magnitude r into a component form, then it is x component is r cos theta, and y component is r sine theta. And this is a vector v, and a into v means to say cos theta minus sine theta cos theta. If you multiply it with this column vector, I take it as a 2 cross column vector. So you will get after simplification, you will get 2 cross again column vector. This is the element is of 2 cross 1, and again you will get two tuples, which is again 2 cross 1. So here you can see after applying T on V, T transformation T on V under this matrix, you will get this. What does it mean? Basically, that translate your position, which is initially over here, with theta angle that is added into alpha. Here you can see, here is not addition, but here after applying T, which is A into V, then in alpha theta is added. In that case, we can say this transformation rotate every vector in counterclockwise about the origin through the angle theta, like this one. So, dear student, this is one of the projection that if you can take any transformation from R3 to R3, in that case, I just take 3 by 3 matrix because order of the matrix will be 3 by 3. If you can take any vector from domain, this one, x, y, z, and if you apply A with V, it can be written as a 3 cross column vector. If you multiply A with V, then you will get X, Y, Z. It means to say this is a projection of 3 dimension onto 2 dimension, and it can be also be written as a 3 dimension with second last component will be 0. So this is just a orthogonal projection of any XYZ coordinate to a XY plane. So, dear student, this is another matrix of a transformation that map matrix of order m cross n to a n cross n. Can you say something? It is just a transpose that convert row to column and column to row. In that case, if I take it as a transformation, it is a transformation from m cross n matrices to n cross m matrices, and T of A is equal to A into transform. If you uh, give any element in domain of order n cross n, if you can, the output will be of n cross m matrix if you can take its transpose. So you have to prove it either it is a linear transformation or not. Just you can see and take it as a homework. So, dear student, today I just give you the idea of linear transformation, and it's one of the fundamental idea. And inshallah, in next classes, I will definitely share some more application of linear transformation, and ultimately we pursue towards our other topics which are depend upon linear transformation and its and rest of the course, and moreover you can see other application of linear transformation in um, even in coding and cryptography. And in cryptography, Hill cipher is one of the application of linear transformation, which more or less we have discussed in our classes. So Hill cipher is again application of linear transformation. So that's all about today lecture. Thank you all and please stay at home. May Allah bless you all. Allah Hafiz.